Hi everyone, welcome back to Chem Help ASAP. We are going to be working through the Chapter 2 example problems in the Open Stax Atoms First textbook. I'll be working through both the example and the Check Your Learning problems. So let's get started with example 2.1, testing Dalton's atomic theory. In the following drawing, the green spheres represent atoms of a certain element. The purple spheres represent atoms of another element. If the spheres touch, they are part of a single unit of a compound. Does the following chemical change represented by these symbols violate any of the ideas of Dalton's atomic theory? If so, which one? Well, I'm not sure how this is showing up on your screen, but these look more like blue spheres here than purple, but we'll go with it. That's fine. We've got two different colors. That's perfectly fine. All right, so what we want to do is we just want to look at this reaction. We've got starting materials and we've got products of the change, and just see if we've violated anything from Dalton's atomic theory. So what I'm noticing first off is I have two green spheres and two blue/purple spheres. But once I get to products, I only have one of each. So I have lost a green sphere and a purple sphere. So in Dalton's atomic theory, it specifically states that atoms are neither created or destroyed in a chemical reaction. But this chemical reaction has destroyed one green one and one purple/blue atom there. So this has violated Dalton's atomic theory, and that's the specific one it has violated, is we must conserve the number and the types of atoms. Okay, so that is problem 2.1. Let's go to the Check Your Learning problem. The Check Your Learning problem reads, in the following drawing, the green spheres represent atoms of a certain element. The purple spheres represent atoms of another element. If the spheres touch, they are part of a single unit of a compound. Does the following chemical change represented by these symbols violate any of the ideas in Dalton's atomic theory? If so, which one? All right, so again, these are looking a little more blue than purple to me. But let's make sure that no atoms are created and no atoms are destroyed. So I have 1, 2, 3, 4 green atoms. So if I check the products, I should have 1, 2, 3, 4. Okay, great. And I have 1, 2 purple/blue spheres. And in my products, I also have 1, 2 purple/blue spheres. So none of Dalton's atomic theory postulates are violated, and this is a valid chemical reaction. Example 2.2, Laws of Definite and Multiple Proportions. A sample of compound A clear colorless gas, is analyzed and found to contain 4.27 grams of carbon and 5.69 grams of oxygen. A sample of compound B, also a clear colorless gas, is analyzed and found to contain 5.19 grams of carbon and 13.84 grams of oxygen. Are these data an example of the law of definite proportions, the law of multiple proportions, or neither? What do these data tell you about substances A and B? Okay, so that was a lot of information there. Let's go ahead and pull our data out and start doing some analysis. All right, first looking at compound A. I'm going to compare the number of grams of oxygen to the number of grams of carbon. And I'm going to do that by dividing the 5.69 grams of oxygen over the 4.27 grams of carbon. This reduces to 1.33 grams of oxygen over 1 gram of carbon. And just for putting this into your calculator and doing the math, if you take 5.69 divided by 4.27, that is where this 1.33 comes from. And of course, that is just over 1. And I'm keeping my grams of oxygen in the numerator and my grams of carbon in the denominator. Okay, so that is for compound A. Let's look at compound B. We will do the same thing. So we've got 13.84 grams of oxygen, and we are going to compare that to the grams of carbon. That is 5.19 grams of carbon. And this reduces to 2.66 grams of oxygen over 1 gram of carbon. Okay, so now what we want to do, now that we have basically simplified our ratios for compound A and compound B, we want to compare compound A to compound B. So I am going to take compound A over compound B, which is simply this ratio for compound A over this ratio for compound B. So it looks a little bit awkward, I know, because we're going to have a fraction over a fraction. But what we want to see is if we get a whole number ratio here. So this is 2.66 grams of oxygen over 1 gram of carbon. And if you do this math, you get that this simplifies to 1 over 2. Now that means that compound B has twice as much oxygen as compound A, which is the law of multiple proportions. Now, you do not have to do the math exactly this way. So let me change color. And if I were to say for compound A, put my grams of carbon on top, I can absolutely do this. And what happens at the end is that I get the reverse ratio here, but I'll show you how that works. So this one is going to simplify to 0.75 grams carbon over 1 gram oxygen. Oh, sorry, I dropped my gram oxygen there. And for compound B, this would be 5.19 grams carbon over 13.84 grams oxygen, and that reduces to 0.375 grams carbon over 1 gram oxygen. And then just like previously, if I take A over B, this is again going to be a little bit awkward. 0.75 grams carbon over 1 gram oxygen. I think I'm just going to put a divide here because I'm a little bit running out of space, but it is the same math that we did previously over 1 gram oxygen. What you'll see is this reduces to 2 or 2 over 1. So we get the same ratio, it's just flipped. So again, this one says that compound A has twice as much carbon per oxygen as compound B. But basically, they both are showing that this is the law of multiple proportions, and you're going to get the same reduced ratio. It doesn't matter if you start with grams of carbon over oxygen or oxygen over carbon. Now let's do the check your learning. A sample of compound X, a clear, colorless, combustible liquid with a noticeable odor, is analyzed and found to contain 14.13 grams carbon and 2.96 gram hydrogen. A sample of compound Y, a clear, colorless, combustible liquid with a noticeable odor that is slightly different from X's odor, is analyzed and found to contain 19.91 grams carbon and 3.34 grams hydrogen. Are these data an example of the law of definite proportions, the law of multiple proportions, or neither? What do these data tell you about substances X and Y? All right, so we're going to do the same kind of math that we did for the previous problem. So let's start this time with compound X. So we have X. And I am going to take the grams of carbon over the grams of hydrogen. Oh, sorry, I didn't label that grams of carbon. My bad. All right. So if I reduce this, I'm going to get 4.77 grams of carbon over 1 gram of hydrogen. Now for compound Y. The important thing when you're doing these problems is to make sure that you are consistent. So because for compound X, I chose grams of carbon over grams of hydrogen, I need to make sure I do the same thing for compound Y. So you'll get things a little bit mixed up if you flip compound Y as a reciprocal of compound X. And then things get a little hairy. And sometimes at that point, it's better to just start over. I have done that many a time with many a chemistry problem. Okay, so that reduces to 5.96 grams of carbon over 1 gram of carbon. All right, so now I am going to take X over Y. And again, this is a little bit awkward because it is a fraction over a fraction, but we want to see what it reduces to. And over our 5.96 grams carbon over 1 gram hydrogen. All right, so when I put this in my calculator, what I get, well, I get a lot of decimals, but that is close enough that you can call that 0.8. Now, 0 point, it doesn't look like anything yet, but if you think about that, that is 8/10 or 8 over 10, which is 4 over 5. So there is our reduced fraction. So this problem supports the law of multiple proportion. It means that even though X and Y are both clear, colorless, they're both combustible, and they both have an odor, they are different compounds. They have a different ratio of hydrogen to carbon or carbon to hydrogen. And just like we did on the previous problem, although I won't work through all the math of it, you can also compare grams of hydrogen over grams of carbon. You will get the same thing, except instead of 4/5 here, you will get 5 over 4, but it will still support the law of multiple proportions. Example 2.3, composition of an atom. Iodine is an essential trace element in our diet. It is needed to produce thyroid hormone. Insufficient iodine in the diet can lead to a development of a goiter, an enlargement of the thyroid gland. And they give us a nice picture of a goiter and iodized salt. The addition of small amounts to iodide to table salt, iodized salt, has essentially eliminated this health concern in the United States, but as much as 40% of the world's population is still at risk of iodine deficiency. The iodine atoms are added as anions, each with a -1 charge and a mass of 127. Determine the numbers of protons, neutrons, and electrons in one of these iodine anions. All right, so we have iodine. Now, they tell us that it has a charge of -1. So I will put the charge in the upper right-hand corner. And then they also tell us that we have a mass number of 127. A mass number goes in the upper left-hand corner. Now, the only other number that I am missing right now is the atomic number, which goes in the lower left-hand corner. So if you find iodide on your periodic table, it is in group 17, it is a halogen, and you will see that it has an atomic number of 53. So that number I got from the periodic table itself. Now we have all the information we need to calculate the number of protons, neutrons, and electrons. So starting with protons, our number of protons is always the easiest because the number of protons is your atomic number. So the number of protons is 53. Remember, your atomic number, i.e. your number of protons, gives the identity of the element. If you change the number of protons, you will change the identity of the element. Now for our neutrons. The way we get our neutrons is we take our mass number of 127 and we subtract our atomic number, which is 53. And this gives us 74 neutrons. Now, the last thing they asked us to do was to calculate the number of electrons. This is where we have to take our charge into account. If we had a neutral atom, then our number of electrons would equal our number of protons, but we do not have a neutral atom. We have a charged species. It's got a charge of -1. Here is where it's really important to remember that electrons also have a negative charge. Though this charge of -1 means that we have one more electron than proton. So our number of protons is 53 plus one more electron, and that gives us 54 electrons. So we have one more electron than proton, which gives us a charge of -1. On to the check your learning. An ion of platinum has a mass number of 195 and contains 74 electrons. How many protons and neutrons does it contain, and what is its charge? I'm going to gather the same information. So we have platinum. They tell us that it has a mass number of 195 and that it has 74 electrons. Now, there's no place on our platinum atom to put 74 electrons, so I'm just going to hold off on that right now. But what we can do is we can get the atomic number. So if you find platinum on the periodic table, it's kind of right in the middle. It has an atomic number of 78. Now what we really want to get is we want to get its charge. So what we're looking for is the number right here in the upper right-hand corner. But first, to help us do that, we are going to calculate protons and neutrons, starting with protons. Remember, the protons are the identity of the atom. They are given by your atomic number, so we have 78 protons. My neutrons tell us what isotope we have. And to calculate that, we're going to take 195 minus our atomic number, and that equals 117 neutrons. Now finally, if we were to calculate electrons, what we would do is we would take our number of protons, which is our atomic number, and we would add whatever our number of electrons is, which we do not know. The problem gives us another piece of information. Remember, it says we have 74 electrons, so I know that this must equal 74. So you can think of this equation more as 78 plus x is equal to 74, and we need to solve for x. Well, solving for x, we're going to get x equals -4. That means we have lost 4 electrons. So we'll call this a loss of 4 electrons. When we have more protons than electrons, it means we have a positive charge. And specifically, we have 4 more protons than electrons. So the charge on this platinum atom is 4 plus. And I can still put my 195 and my 78 just to make it complete. Example 2.4, calculation of average atomic mass. A meteorite found in central Indiana contains traces of the noble gas neon picked up from the solar wind during the meteorite's trip through the solar system. An analysis of the sample of the gas showed that it consisted of 91.84% neon-20 with a mass of 19.9924 AMU, 0.47% neon-21, which has a mass of 20.9940 AMU, and 7.69% of neon-22, with a mass of 21.9914 AMU. What is the average mass of the neon in the solar wind? So if you are familiar with weighted averages, this is what we are going to calculate. We are going to calculate a weighted average, which means we are going to take each of our masses multiplied by our percents, and that will give us our average. The only trick here is all of our percentages need to be taken out of percent and made into just decimals. Well, that's very easy to do. All you do is divide each of them by 100. So I'm going to start with neon-20. Now its mass is 19.9924. So I'll put that down, 9924 AMU. I'm going to multiply that by its percentage turned into a decimal. So instead of 91.84%, I'm going to move that decimal 2 places to the left, and there is my decimal. So I hope that makes sense. All I've done is I have divided by 100 to convert it from a percent to a decimal. Okay, so that is my first term for neon 20. Now I need to have my term for neon 21. So the mass of neon 21 is 20.9940 AMU. Again, I'm going to take this 0.47% and convert it into a decimal. So I'm going to take that and divide by 100, which means I push that decimal to the left 2 places. I know it's a very small number. That's all right. No problem. And now I'm going to take my neon 22 term right here. Here is its mass. It has a mass of 21.9914 AMU. And again, I'm going to take the percentage here and turn it into a decimal. So I'm going to divide by 100. And I'm just going to barely squeeze it in there. That is 769 there. Okay, so now I just want to know what this equals. So I'm just going to multiply each of these terms and add it together. And my calculator gives me a lot of decimal places. So I am going to put quite a few of these down. That is AMU. And we need to round to the correct decimal place, which means we are rounding to this 5. And so there's a 0 after it. So this rounds to 20.15 AMU for our average mass of neon in the solar wind. Now for the check your learning. A sample of magnesium is found to contain 78.7% of magnesium-24 atoms, and this has a mass of 23.98 AMU. 10.13% of magnesium-25 atoms, and these have a mass of 24.99 AMU. And 11.17% of magnesium-26 atoms, and those have a mass of 25.98 AMU. And we're going to calculate the average mass of a magnesium atom. So once again, we are going to do a weighted average. So starting with my magnesium-24, I'm going to use the mass that they gave me. So this is 23.98 AMU. And again, I'm going to convert this percentage into a decimal just by dividing by 100. So this is 0.7870. I just moved that decimal 2 places to the left. Now I'm going to add in my term for my magnesium-25. Its mass is 24.99 AMU. And its percentage is 10.13. Again, converting that to a decimal means my decimal is 0.1013. Plus my last term for my magnesium-26. It has a mass of 25.98 AMU. And my percentage is 11.17, so converting that into a decimal, 0.1117. All right, so now I just plug all this into my calculator, and that will give me my average mass. Again, I get a lot of decimal places. I want to make sure I round to the correct decimal place, and I need to round to the second decimal place right here. And so my final answer is 24.31 AMU. Example 2.5, calculation of percent abundance. Naturally occurring chlorine consists of chlorine-35 with a mass of 34.96885 AMU and chlorine-37 with a mass of 36.96590 AMU, with an average mass of 35.453 AMU. What is the percent composition of chlorine in terms of these two isotopes? So this again is a weighted average, but in this case, they gave us the average mass and they want us to figure out the percentages of chlorine 35 and chlorine 37. I'm going to start by just writing out my weighted average and putting in what I know and then just putting in a variable for what I don't know. So I know my mass of chlorine 35. That is 34.96885 AMU. Sorry, that 8 did not quite connect. And this is going to be my abundance of chlorine 35. So I'm just going to write that as chlorine 35. Remember, we would take the percentage and turn it into a decimal. I would take this term, I would add it to my chlorine 37. Again, I'm given the mass for that. That is 36.96590. And again, I would take the percent abundance of chlorine 37 multiplied by the mass, and this would give me my weighted average. Well, we actually have our average mass right here. So we do have a number for that. 53 AMU. Okay, so what we've got here is we've got an equation with two variables. Well, we can't solve for two variables with one equation, so there must be more information that we know, even though nothing else is explicitly stated in the problem. That other piece of critical information is that the percent of chlorine 35 plus the percent of chlorine 37 equals 100%. Or you can think about this as chlorine 35, not the percent, but the decimal amount, which we put here, plus how much chlorine 37 we have is going to equal 1. So now what we can do is we've got two equations, two unknowns, and we can solve a system of equations. There are multiple ways algebraically to do this, and you can choose whichever way makes the most sense to you. What I am going to do is I am going to solve this equation for chlorine 37 and then substitute it into the original equation. So if I'm going to solve this guy for chlorine 37, it means that chlorine 37 equals 1 minus my amount of chlorine 35. So this quantity right here, I'm going to put in these parentheses right here. So my original equation, I'm just going to rewrite it. So my first term does not change. This still stays chlorine 35. This mass also does not change. And now instead of chlorine 37, I'm going to put in this quantity, i.e. 1 minus my amount of chlorine 35. And of course, this still equals my original weighted average, which is 35.453 AMU. And once again, I have dropped my AMU here. I am so sorry. All right, so now we have one equation, but we only have one variable, so we can solve this equation for our amount of chlorine 35. So first, let's distribute through in this term so we can simplify. And just for simplicity's sake, I am going to drop now the AMU just so we deal with our numbers and our variables. Of course, you do not have to. I just want to write a little bit less on the screen. Okay, so our first term here again is still unchanged because we're really looking at our second term and distributing our second term. Okay, so we have plus. Now we're going to have our 36.96590 times 1, which of course is just going to give us our 36.96590. And then we are going to have this 36 times a negative chlorine 35 here. And I'll show you what that looks like. So positive and negative, that gives me a negative. And this is going to be 36.96590. and I'm just going to put my 35 chlorine here, and this still equals our 35.453. Now, what you can do at this point, if you want, if it makes more sense, is instead of writing chlorine 35, if this is confusing you, you can always just make it X, and all you're doing is solving for X. It really is, write it in a way that makes the most sense to you. Okay, so now that I have this, I'm going to combine like terms. So I need to find my like terms, and we're just going to do this stepwise. So what I'm seeing is I have like terms here. Both of these have my variable, have my chlorine 35. So let's go ahead and combine these like terms. So now what I've got is a negative 1.99705. And again, this is times my variable. You can always use X if that makes more sense. And I'm still just carrying these other terms through. So I'm just working on simplifying here. 590, and this is still equaling 35.453. Okay, so now what I need to do is I need to simplify again and combine like terms again. Now you could do this in one step if you want. That's totally fine. I just happened to break it up into two. So I have these two terms which are constants, so I am going to combine them. And what I've got now is negative 1.99705 times my variable, and that equals negative 1.5129. Okay, so all that's left is to divide both sides by negative 1.99705, and what I get is, I'm going to put this over here, the value for my chlorine 35 is 0.7576. Now remember, this is a decimal, so if you wanted to, well, the problem asks us to convert it to a percent. So if I need to convert this to a percent, I'm just multiplying by 100%, which is 75.76%. So that takes care of my chlorine 35, but I still have to find chlorine 37. But at this point, you can either take your decimal and 1 minus your 0.7576, or what I'm going to do is I'm going to actually use this equation right here, and I'm going to put this calculation up here. So I know my percentage for chlorine 35 is 75.76%. plus my percentage for chlorine 37, and that equals 100%. So therefore, the percent of chlorine 37 is equal to 24.24%. So I know this problem maybe seemed daunting at first, and the key thing I think here to remember is that you know more information than you think, and specifically you know that these two isotopes must add up to be 100%. Now for the check you're learning. Naturally occurring copper consists of copper 63 with a mass of 62.9296 AMU and copper 65 with a mass of 64.9278 AMU with an average mass of 63.546 AMU. What is the percent composition of copper in terms of these two isotopes? So we are going to tackle this exactly the same way. So first, I'm just going to write what I consider my main equation, where I'm going to take my mass of copper 63, which is 62.9296 AMU, and this would be multiplied by how much copper 63, again converted into a decimal, plus my term for my copper 65, which has a mass of 64.9278 AMU, and we don't know its average mass, so I'm just going to put that right there, and of course this equals my total, my average mass of 63.546 0.46 AMU. And just like in the previous problem, the other piece of information that we have that maybe we don't realize we have is that our percent of copper 63 plus our percent of copper 65 is equal to 100%. Now we're using decimals in here, so I'm going to convert these percentages to decimal. So that means my amount of copper 63 plus my amount of copper 65 is going to equal 1. Okay, so I am going to solve again for my amount of copper 65. So if I'm going to take this equation and solve for copper 65, that will give me copper 65 is equal to 1 minus my copper 63. And then I'm going to take this quantity and plug it in right here, and that should eliminate one of my variables. Okay, so going rewriting my main equation with my substitution. My first term stays exactly the same. This is still copper 63. But now I'm going to take my copper 65 and I'm going to plug in this, what I just solved for. And this still equals my 63.546 AMU. So now again, I have one equation, one variable. I just need to solve for it. So let's go ahead and distribute right here. And again, I'm going to just drop my AMU for simplification's sake, but of course those units do not go away. I'm just saving a little bit of time and space by not writing them down. Okay, this term still stays the same. And now I'm going to have the 64.9278 times 1, which is just 64.9278 minus this term times my copper 63, which is 64.9278 times copper 63, and this again still equals our 63.546. So now it's time to combine like terms. So let's find our like terms here. So we have our two variable terms, which are like terms, and we have, I'll do this a wiggly line, our two constant terms. So we're going to combine our variable terms and we're going to combine our constant terms. And that will give us negative 1.9982 times copper 63, and that is going to equal negative 1.3818. Sorry, that decimal did not come through. Okay, so solving for copper 63, we get 0.6915, which if we convert into a percentage is 69.15%. Okay, that's fantastic. All we need to do now is find our percent of copper 65, and that is not really a whole lot of space up there, so I think I'll find that percentage down here. So if we take our percent of copper 63, which is 69.15%, again, I'm just plugging into this equation here, plus our percentage of copper 65, and that equals 100%. Now solving for copper 65, our percent of copper 65 is equal to 30.85%. Example 2.6, empirical and molecular formulas. Molecules of glucose, blood sugar, contain 6 carbon atoms, 12 hydrogen atoms, and 6 oxygen atoms. What are the molecular and empirical formulas of glucose? Okay, well, let's start with the molecular formula because they give us all of the atoms. So we're starting with our carbon atoms, and they tell us we have 6 of them. So remember, the 6 becomes subscripted. For our hydrogen atoms, the symbol for hydrogen is H, and we have 12 of them, again, subscripted. And then we have 6 oxygen atoms. So that is O with a 6 subscripted. So this is the molecular formula for glucose. Now they also want the empirical formula. It's important to remember the difference between molecular and empirical formula. Your molecular formula tells you how many atoms the molecule has. Your empirical formula gives you your lowest common ratio for all of those atoms. So if I'm looking at these 3 numbers, 6, 12, and 6, is there a common multiple that I can divide these by? And the answer is yes, I can divide each of these numbers here by 6. So that would give me carbon, and a 6 divided by 6 is just 1, which we don't write. Hydrogen would be 12 divided by 6, which is 2, and oxygen, which would be 6 divided by 6 again, which would just be 1 oxygen. Again, for the ones for carbon and oxygen, we do not write 1 there. It is assumed to be 1 if no number is written. So this is our empirical formula. It is the lowest ratio, and up here is our molecular. On to the check your learning. A molecule of metaldehyde, a pesticide used for snails and slugs, contains 8 carbon atoms, 16 hydrogen atoms, and 4 oxygen atoms. What are the molecular and empirical formulas of metaldehyde? Okay, so again, I'm going to start with the molecular formula because they gave us the numbers of all of the atoms. So for carbon atoms, we have 8. For hydrogen atoms, we have 16, and for oxygen atoms, we have 4. This is the molecular formula. Now, to determine the empirical formula, what we want to know is between 8, 16, and 4. Is there something we can divide it by to reduce this ratio? Well, yes, we can divide each of these numbers by 4, and that will give us the empirical formula. So if I'm dividing by 4, 8 divided by 4 is 2. 16 divided by 4 is 4. And 4 divided by 4 is 1, which we just leave blank. We leave it alone. This is the empirical formula. And it is the lowest ratio. Example 2.7, deriving moles from grams for an element. According to the nutritional guidelines from the U.S. Department of Agriculture, the estimated average requirement for dietary potassium is 4.7 grams. What is the estimated average requirement of potassium in moles? Okay, so what we're going to do is we're going to take our grams and we need to convert it into moles. Now, whenever we're going back and forth between grams and moles, the important thing is to have the molar mass. Now, because this is just an element, potassium, we can find the molar mass in the periodic table. So if you find potassium in the periodic table, so on the far left-hand side, atomic number 19, that is what we're going to use to do this conversion. So I'm going to start with what I was given, my 4.7 grams. Now I want to put this molar mass in such that my grams cancel and I'm left with moles in the numerator. So what I like to do is I like to put my units in first. So this is actually grams of potassium and moles of potassium, and then I put my numbers in. Remembering, of course, that when you have molar mass, it's always per 1 mole. Now, the number I put in here is the number of grams in 1 mole of potassium, and that is given on the periodic table. So that is 39.10. And then I simply divide here, and what you can see is that my grams have canceled and I am left with moles in my answer, which is exactly what I wanted. So that will give me 0.12 moles of potassium. Now on to the check your learning. Beryllium is a light metal used to fabricate transparent X-ray windows for medical imaging instruments. How many moles of beryllium are in a thin foil window weighing 3.24 grams? Okay, so again, we are given grams and we want to convert to moles. To do that, we need the molar mass of beryllium. And again, because it's an element, we can just go to the periodic table for that. So starting with our 3.24 grams of beryllium, I want to make sure I get my units in first and they are in the correct place. So I want my grams of beryllium to cancel. So I'm going to put that in the denominator. And I'm converting to moles of beryllium, so that goes in the numerator. Now I'm going to put my numbers in. Again, molar mass is always per 1 mole, and my number of grams is given by the periodic table. That is 9.0122. So now I just do my math, and what's going to happen is my grams of beryllium are going to cancel. I'm left with moles of beryllium, which is exactly what the problem asked me for, and I get 0.360 moles of beryllium. Example 2.8, deriving grams from moles for an element. A liter of air contains 9.2 times 10 to the negative fourth moles of argon. What is the mass of argon in a liter of air? Okay, so we're just going the other way now. So I'm going to take my moles of argon and I want to convert that into grams of argon. Now this is again for an element, so I can find my molar mass on the periodic table. So starting with what they gave me 9.2 times 10 to the negative fourth moles of argon. And again, I'm going to put my units in first and then I'll put my numbers in. So this time I want my moles of argon to cancel, and I want to go to grams of argon. Now I'm going to put my numbers in, remembering that molar mass is always per 1 mole. And then looking at the periodic table, I will see that 39.948 grams of argon is in 1 mole of argon. And this setup allows the moles of argon to cancel and gives me grams of argon. So putting this into my calculator, I get 0.037 grams of argon. For the check you're learning, what is the mass of 2.516 moles of gold? Okay, so I'm given moles of gold. I want the mass, which means I want to go to grams. Okay, so I was given 2.561 moles of gold. Again, because it's an element, all I need is the periodic table, but let's get my units in. So I want the moles to cancel. So I'm going to make sure that's in the denominator. I'm going to grams of gold. Now I'm going to put my numbers in. So here is my 1 mole. And according to the periodic table, the mass is 196.9665 grams per 1 mole. And again, just checking, make sure your moles cancel. And this gives me 504.4 grams of gold. Example 2.9, deriving number of atoms from mass for an element. Copper is commonly used to fabricate electrical wire. How many copper atoms are in 5 grams of copper wire? Okay, so in this problem we are given grams and we're asked to calculate how many atoms. So this is going to be a 2-step process, but I will also show you how to calculate it in 1 step, but you'll get the same answer no matter which way you do it. So starting with my 5 grams of copper, I'm going to first convert this into moles. Again, because it's an element, my molar mass is on the periodic table, so let me get my units in. I want my grams of copper to cancel, and I want to get moles of copper out. So remembering it's always per 1 mole. Looking at the periodic table, the molar mass is right here per 1 mole. And so actually I'm going to put the equals down here. So this gives me 0.0787 moles of copper. And just it's always nice to double check that your grams of copper canceled and you're left with moles of copper in the numerator. Now, we're not quite done with this problem because it didn't ask us for moles of copper, it asked us for atoms of copper. So this is where we want to use Avogadro's number, because Avogadro's number allows us to convert between moles and atoms. Either, in this case, we're going moles to atoms, or it can take you from atoms to moles. So I'm going to start with my moles of copper that I just calculated. And again, I like to put my units in first before I put my numbers in. I want to make sure my moles of copper cancel. So this is going to go in the denominator. And I am converting into atoms of copper. Now, Avogadro's number is always per 1 mole, and specifically it is 6.022 times 10 to the 23rd atoms of copper. Again, make sure that your units cancel. It's very easy to get these flip-flopped and to have the right idea in your mind, but end up doing the wrong calculation. That's why I always like to put my units in first. Okay, so doing this calculation, I get 4.74 times 10 to the 22nd atoms of copper. And this does make sense. We should get a very large number of atoms. So sometimes if you're working through these problems quickly and like you get this conversion factor flipped, you'll get a very small number here. This will usually be to a negative exponent. That should be a red flag that something is not quite right. You should have a lot of atoms. Now to show you how to do it in one step. I'm going to need a little bit more space, so I'm actually going to write on the picture here. So we still start with our 5 grams of copper. Again, I want to convert out of grams of copper. I want to go to moles of copper. Put my units in first. This is per 1 mole, and this is 63.545. That got a little bit squashed, didn't it? Then instead of actually doing that calculation, I'm just going to continue on, and I'm going to make sure that my moles of copper cancel. So this is where I'm going to use Avogadro's number. Again, I'm just putting units in first. So I want to make sure my moles of copper cancel, and I am left with atoms of copper in the numerator. Let me extend that. Avogadro's number is always per 1 mole, and this is 6.022 times 10 to the 23rd. So what I want to point out here, and I'll do it in red, is that my grams of copper canceled, and then my moles of copper canceled, and all I have left now is atoms of copper, which is exactly what I want. So this, of course, equals the exact same number. You just did it in one step instead of 2. Atoms of copper, that is a 2. Again, either way, just make sure it makes sense to you. Check your learning. A prospector panning for gold in a river collects 15 grams of pure gold. How many gold atoms are in this quantity of gold? So again, we're going to start with grams, and we want to go all the way to atoms. And we can do this in either 1 step or 2 steps. I'm going to start with the 2-step process, and then I'll show you the 1-step process. So starting with my mass of gold. So I have 15 grams of pure gold. Putting my units in first, I want to make sure my grams cancel, and I'm left with moles of gold. This is a 1, and this is 196.9665. And that gives me 0.07616 moles of gold. But of course, I'm not finished yet because I need to go from moles of gold into atoms of gold. So taking that 0.07616 moles of gold, I need to convert it into atoms of gold. So units first, I want to make sure my moles cancel, and I am going to go to atoms of gold. And using Avogadro's number, that is going to be per 1 mole. And up here goes to 6.022 times 10 to the 23rd atoms. So again, I have not shown my units. So my grams canceled up here, and now my moles cancel down here, and I'm left with atoms, which is what the problem asked me for. And I get 4.586 times 10 to the 22nd atoms of gold. Okay, great. And let me show you the one-step process as well. We still start with our 15 grams of gold. Again, we want our grams of gold to cancel. We're going first to moles of gold using the molar mass. So that is a 1. And this is a 196.9665. And then not stopping to do that calculation, we're going to now cancel our moles of gold. So that is going to go in the denominator. And atoms is going to go in the numerator. So this is Avogadro's number. 2 times 10 to the 23rd. And just always before you put these in your calculator, just make sure that your units cancel like you expect them to do. I have made many an error by not checking my units. 10 to the 22nd atoms of gold. Example 2.10, deriving moles from grams for a compound. Our bodies synthesize protein from amino acids. One of these amino acids is glycine, which has the molecular formula of C2H5O2N. How many moles of glycine molecules are contained in 28.35 grams of glycine? Okay, so what we want to do is we want to take these grams of glycine and convert to moles. Well, unlike elements, we cannot find the molar mass of glycine on the periodic table. We must calculate it. So that is the first thing that I am going to do here, is I am going to calculate my molar mass. And to do that, I need the molecular formula, which is given right here. So I'm just going to work left to right here. So I'm going to start with carbon. There are 2 carbon atoms. So that is going to be 2 times my molar mass for carbon. Again, I'm getting my molar mass for carbon from the periodic table. And that is 12.01 grams per mole. Now onto hydrogen, I have 5 of them. And my molar mass of hydrogen is 1.0079 grams per mole. And then on to oxygen, I have 2 oxygen. The molar mass of oxygen is 15.9994 grams per mole. And then finally nitrogen, and I only have 1 of these. So sometimes you'll see people will leave off the 1 up here, which is totally fine. Okay, so I am going to add all of these up, and that will give me my molar mass for glycine, which is 75.067 grams per mole. Now that I have the molar mass, I can convert my 28.35 grams of glycine into moles of glycine. So starting with my 28.35 grams of glycine, Again, I want to make sure that my grams cancel, so I'm going to put my grams of glycine in the denominator and my moles of glycine in the numerator. Now remember, when I write grams per mole like this, it really can be maybe more explicitly written grams per 1 mole. It's just that this is a lot easier and quicker to write, but it means the same thing as this. So that means when I'm putting my molar mass in here, the 1 goes here, and the 75.067 grams goes in the denominator. Okay, so now you can see that my grams of glycine are going to cancel, and I'm going to be left with moles of glycine, so I can go ahead and do this calculation, and I get 0.3777 moles of glycine. Now, the one thing I will point out is that the text only gives 3 sig figs for this answer and not 4 sig figs, but our molar mass here has 5 sig figs, and they gave us 4 sig figs here. So really the answer should have 4 sig figs, not 3. Check your learning. How many moles of sucrose, C12H22O11, are in a 25 gram sample of sucrose? Okay. So again, I'm going to have to calculate a molar mass here because I have grams and I want to get to moles. So I'm going to do the same kind of calculation. I'm just going to work left to right and find the molar mass for sucrose. So I have 12 carbon atoms. So I'm going to do 12 times the molar mass of carbon. So that is 12 times 12. I have 22 hydrogen atoms. Again, the molar mass of hydrogen is grams per mole. And then finally, oxygen, I have 11 oxygens. And the molar mass of oxygen is 15.9994 grams per mole. And I'm going to add all of this up, and I get 342.2992 grams per mole. Again, remembering that this is the same thing as writing it like this. And sometimes when you're first starting out and you're calculating molar mass, it can be helpful to write it like this so that you keep in mind what goes in the numerator and what goes in the denominator, because this 1 mole down here is often forgotten by students who are just starting out. Okay, now I can take my 25 grams of sucrose and convert to moles. So if I'm going to convert this to moles, then I want to make sure that my grams of sucrose is in the denominator here, and I have moles of sucrose in the numerator. So this is 1 mole and 342.2992 grams. Again, double checking my units. The grams of sucrose cancel, and I'm left with moles of sucrose, which is what the problem asked for. And so when I do this calculation, I get 0.073 moles of sucrose. Example 2.11, deriving grams from moles for a compound. Vitamin C is a covalent compound with the molecular formula C6H8O6. The recommended daily dietary allowance of vitamin C for children aged 4 to 8 is 1.42 times 10 to the negative 4th mole. What is the mass of this allowance in grams? Okay, so we have been given moles and we want to convert to grams, which means we need the molar mass for vitamin C, which means we need the molecular formula, which is given right here. Okay, great. So the first thing I'm going to do is I'm going to calculate the molar mass of vitamin C based on the molecular formula. So I have 6 carbon, 1 grams per mole. I have 8 hydrogen, 0.079 grams per mole. And I have 6 oxygen. And that is 15.9994 grams per mole. So what you're going to find after you calculate so many molar masses is you're going to start inadvertently memorizing the molar mass of a lot of these elements. Okay, so if I do this calculation, I get a molar mass of here grams per mole, remembering, of course, that I can also write it like this, just to give a little bit of clarity. All right, so that is the molar mass for vitamin C, which means I am now ready to convert these moles into grams. So starting with what they gave me, mole of vitamin C. I'm going to put my units in first. I want my moles of vitamin C to cancel, and I want to go to grams of vitamin C. So now again, this is where it's easier to see it like this. That's 1 mole and 176.1256 grams. You can see that my moles cancel. I'm left with grams. And, whoops, I'm going to put this underneath. If I do this calculation, I get 0.0250 grams of vitamin C. Check your learning. What is the mass of 0.443 moles of hydrazine, which is N2H4? Okay, so I've been given moles. I want to go to grams, which is mass. But hydrazine, I'm going to have to calculate the molar mass. So I have 2 nitrogen atoms. So nitrogen's molar mass is about 14. And I have 4 hydrogen atoms. Okay, this one is a pretty quick one to calculate, and I get 32.045 grams per mole, remembering that I can also write it like so. Okay, now I'm ready to convert from moles into grams. So I have 0.443 moles of hydrazine. So I want to make sure that my moles of hydrazine go in the denominator here, and this is grams of hydrazine. Okay, so that's 1 mole and 32.045 grams. Make sure your units cancel, and that gives me 14.2 grams of hydrazine. Example 2.12. Deriving the number of atoms and molecules from the mass of a compound. A packet of artificial sweetener contains 40 milligrams of saccharin, which has the structural formula, this huge guy right here. Given that saccharin has a molar mass of 183.18 grams per mole, how many saccharin molecules are in 40 milligrams, or a 0.0400 gram sample of saccharin? How many carbon atoms are in the sample? Well, the nice thing is they went ahead and gave us the molar mass, which is fabulous, so we don't have to calculate it. But we do need to calculate how many saccharin molecules and then how many carbon atoms. So let's deal with the saccharin molecules first. Okay, starting with our 40 milligrams of saccharin, or our 0.04. 0.0400 grams of saccharin, H5NO3S. That is a 5. Okay, so the first thing I need to do is I need to convert this into moles, and then I need to go into molecules. All right, so I have been given the molar mass, but again, make sure that your units are where you want them to be. So I want to make sure that my grams of saccharin cancel. So I'm going to make sure that those are in the denominator. And I am going to moles of saccharin. All right, so this is going to be per 1 mole, and they gave me my molar mass, which just helps because it saves me a step. Okay, so what's going on here is, remember my grams have canceled. I now have moles, but of course I don't want to stop at moles because the problem asked me for molecules, which means I need Avogadro's number. But first I'm going to make sure that my moles are going to cancel here. So I'm going to make sure that moles of saccharin are in the denominator so that I do not flip-flop this conversion factor. And then that's going to put molecules in the numerator. Okay, so for Avogadro's number, of course, it's per 1 mole. And this is 0.22 times 10 to the 23rd. And now you can see that my moles of saccharin have canceled, and this will give me molecules of saccharin. So let's do this calculation. And what I'm going to do is I'm actually going to put this number right up here. Okay, so if you put this in your calculator, what you get is 1.31 times 10 to the 20th molecules of saccharin. All right, so that is the first part done. Now the second part asks us how many carbon atoms are in the same sample. Okay, so we're going to take our molecules and figure out how many carbon atoms. Well, this is where it's really helpful to have the molecular formula, or of course they gave us the structure too. So in one molecule of saccharin, there are 7 carbon atoms. So for each molecule that we have, we're going to get 7 carbon atoms. So that is our conversion factor to go from molecules of saccharin to atoms of carbon. And I'm going to write this in the picture because I'm going to need space. So I'm just taking my number of molecules of saccharin and I'm going to convert it into atoms of carbon. So for every 1 molecule of saccharin, there are 7 carbon atoms. And that will give me my total number of carbon atoms, and that is 9.20 times 10 to the 20th carbon atoms. Again, you can see that my units do cancel properly. So one thing when you have a lot of calculations like this, even though it feels like a pain to write out these units, they're really long, it makes sure that you keep your calculation in the right order and that you don't flip a conversion factor, and then you can be sure that you've got the right unit when you are finished. Check your learning. How many C4H10 molecules are contained in 9.213 grams of this compound? And then how many hydrogen atoms? Okay, so what we need to do if we're going to go from grams to molecules is we are going to need the molar mass. Well, they gave us the molecular formula, so we are going to have to first calculate the molar mass. So let's do that. So I have 4 carbon atoms, and I have 10 hydrogen atoms, And that gives me a molar mass of 58.123 grams per mole. Okay, so starting with my 9.213 grams, I'm going to first convert that to moles. So I have 9.213 grams C4H10. Let's make sure my units cancel out properly. So this should be grams in the denominator and moles in the numerator. So that's 1 mole and 58.123 grams. Great. Except I'm not finished because I have to go to molecules. So I'm going to need Avogadro's number. All right, so this time I want my moles to cancel. And I am going to molecules. And let me just extend that out a little bit. Okay, so Avogadro's number is always per 1 mole. And of course, this is 6.022 times 10 to the 23rd molecule. So let's just double check our units. Our grams have canceled, then our moles canceled, and so this will give us molecules of C4H10, which is what the problem asked us for. Okay, so putting all of this into my calculator, I get 9.545 times 10 to the 22nd. This is molecules of C4H10. Okay, but the problem also asked me how many hydrogen atoms. Well, the thing I need to remember is that in one molecule of C4H10, there are 10 hydrogen atoms. So that is going to be my conversion factor. So starting with my molecules, which I just calculated, this is molecules of C4H10. I want to make sure that my molecules cancel. And I am going to hydrogen atoms. And so for every 1 molecule of C4H10, there are 10 hydrogen atoms. So this is simply 9.545 times 10 to the 23rd hydrogen atoms. And that is the last problem in Chapter 2. I hope you found this helpful. Thanks so much for watching.